welcome to Algebra II with Mr. Clausen. So we're going to talk about simplifying complex fractions today, which is just a continuation of the video that we did yesterday that I separated out just to make sure that you had the previous content first. And so what we're going to do today is just go over a couple examples of simplifying complex fractions, so you can just go through these with me and get a general sense of what we're looking at today. And really, what a complex fraction is a fraction in which there is a given fraction in a numerator of a already included fraction, or maybe the denominator of an already included fraction, or both the numerator and the denominator. And so the idea here is that generally we don't like things being in this complex fraction format. So what is typically done is that they are simplified to some extent. And so how we do this is relatively simple. You know, if we rewrite this given expression, it might be a little easier to look at like this, where we go and, you know, we think about these two fractions. I mean, this is just y over 1 and this is 1 over x. And there's two different ways that we can look at this. So we can either go and explain that the least common denominator between 1 over x and 1 or y over 1 is simply, or least common multiple, x times 1. And this could be solved in a relatively simple fashion by just going and saying, like, all right, if we want to simplify this out, we can go multiply both the numerator and the denominator by the least common multiple, and then as a result, you know, this x will cancel with that x. Don't cancel this x with that x, you just undo what you did. And then you'd have a 1 left, and then y times x. And so you'd have 1 over xy, or yx, depending on how you want to do it. And that would be your simplified expression. Now, another way that you could do this is that if you know, see a situation like this, and it's simple enough that you feel like you can, you know, sort through it, or you feel comfortable with, you know, doing this denominator application like this, you know, you can go and say 1 over x is all over y over 1, and say 1 over x, because this is just like a division bar here, so to speak, and you can say divided by y over 1, rearrange that based on knowledge that you have on multiplication, and still get the 1 over xy. So there's a couple different ways that you can look at this. And again, part of the reason I split this video up so that you can kind of feel your way through this simplifying process. This might seem super simple and intuitive to you. Some of you might be like, man, I've never really thought about it that way, and I'm not sure if I can do that consistently. So there will be plenty of examples in the homework where you can put this to practice and get some comfort with this. So now let's look at a little bit more elaborate example here in terms of a given homework set. So here, this is the fraction that we have. So 2y is obviously the, you know, least common multiple that we have to deal with here, because it's the only fraction that is in place here. And so this is a relatively easy fix. So I just go and I multiply both the numerator and the denominator by this least common multiple. Since this is a entire denominator, all right, there's no like separation here where we're adding or simplifying these fractions. This would have to be distributed to both. And so typically what happens here is that, you know, those cancel out. And so what you'll get is you'll get 3 times 2y. Okay, so that's our numerator. That's this going to this. And now when we multiply 2y by 1, that's obviously going to give you 2y. And if we go 2y times 1 over 2y, well, those should just cancel and give you the numerator left over, which is -1. And so we can go write this as 6y over 2y minus 1. And we get this really nice simplified expression. Now, I can take a minute and look at this, and maybe before multiplying everything back together, just make sure that everything is connected and in place, or couldn't be simplified even further by, let's say, canceling like 2's here or something, but this is a 1, so we can't factor out that 2. But just working through to get rid of that pesky fraction. That pesky fraction in the denominator of this fraction is what makes it complex. And they happen. They could be there for very good reason in a real-world application, but generally when you go and then cycle this through and you put it in a textbook, or you use it in an industrial application, or you're punching out some financials in QuickBooks, you would rather have it in this type of format. At least you would rather have it that way if you're doing thousands upon thousands of those calculations, which is what we want to take advantage of in algebra. So now let's go and dig into this really fun, gross, wow, not gross, because you're going to have some tools at your disposal, examples here as far as what we got going on. And so with this example, what I'm going to do first is I'm going to separate these two halves apart and combine everything into one term in the numerator and one term in the denominator. Now, there'll still be fractions in the numerator and denominator, but we're going to apply our knowledge of subtraction of rational expressions here and get this sorted through a little bit. So if we look at this example here and we separate this out and say x minus 2 all over x and minus 2 over x plus 1, what I want to point out here is the least common multiple is going to be x times x plus 1. And so if we look at that given circumstance, what we're going to do here is we're going to multiply this half by x plus 1 all over x plus 1, and then multiply this side by x over x. That'll give everything to the same least common multiple, and then we'll have x minus 2, and then we'll have, and we'll need to multiply that by x plus 1 minus 2 times x all over the x times x plus 1 format that we are doing here. If we do a little bit of foiling, we'll see that this gets us x squared minus x minus 2. All right, and we'll have minus 2x there. So then we'll have x squared minus 3x minus 2 all over x times x plus 1. And I'm going to leave the rest here for now in terms of this operation, because that should just work out fine. And now what we have here is we'll go and say 3 over x minus 1 minus 1 over x plus 1. Well, I can very clearly see that the LCM in this case is x minus 1 and x plus 1. Should be simple and straightforward here. So multiply this side, multiplication by x minus 1 by x minus 1. And again here by x plus 1 and x plus 1. That way we're getting the denominators on both of these terms to be equal. And now we'll get 3 times this x plus 1. This will get us 3x plus 3. And then we'll get 1 times x minus 1, which should get us minus x minus 1, because it's just times 1. Make sure you put that minus sign in the right place so that you can distribute accordingly. And then you'll have x minus 1 and x plus 1 as your factors. All right. And we can simplify this out a little further. 3x minus x and 3 plus 1. So that'll give us 2x plus 4, which could be simplified out a little bit. If we have x minus 1 and x plus 1, let's see, that might be worth just checking real quick. I don't think that's going to do anything meaningful. I mean, we could split this apart and say 2 times x plus 2. Yeah, that doesn't really do anything for us at the moment. Maybe worth keeping in mind, but this is the denominator and this is the numerator. So now that we've simplified this out a little bit and have combined these two different rational expressions and simplified them into one, we can now say x squared minus 3x minus 2 all over x times x plus 1. And this will be all over 2x plus 4 times x plus 1, x minus 1. So now what I would like to do here is just go and rewrite this accordingly by saying x squared minus 3x minus 2 all over x times x plus 1. And we divide this by the, sorry, I don't want to write that there. And then divide that by 2x plus 4 divided by x plus 1 and x minus 1. We can create this from this. It's the same thing. And then if we apply the division, what this should look like now is x squared minus 3x minus 2. And then we can say x times x plus 1 times x plus 1 times x minus 1, and then put that all under 2x plus 4. And we have a term that'll cancel out here. But in the end, what your solution will look like is, it is a little bit more haphazard here than normal. We would have to factor in this trinomial with this binomial if it doesn't cancel out in any way, and then distribute this x across here. So we're just going to write that solution up here. And so we'll go x times x squared will be x cubed. X times negative 3x will be negative 3x squared. X times negative 2 will be negative 2x. Negative 1 times x squared will be negative x squared. Negative 1 times negative 3 will be positive 3x. And negative 1 times negative 2 will be positive 2. And so once we add up everything for the numerator, we'll get x cubed minus 4x squared plus x plus 2. And that'll be our numerator. And then if we go and distribute this accordingly, we should get 2x squared plus 4x. And this will be the complex fraction simplified completely in this given situation. So with that said, I hope that this video gave you a nice breakdown of how to look at these complex fractions from simple examples to more complex examples, and just gave you at least a visual pathway. Some of you may be able to visualize this more quickly and get through steps in a much quicker fashion. That's fine. You know, we're just trying to visualize and build that understanding. And with that said, let's do some math.